Welcome back. In this next video, we're going to go ahead and continue configuring the MPLS backbone. We'll go ahead and work on PE1 and PE2 some more, and this time we'll be configuring routing. So let's go ahead and look at the Detailed Network Topology tab. And on here, to zoom in just a little bit also, we're going to go ahead and build OSPF adjacencies between PE1 and PE2. Be doing this across the gig 00 link and gig 000 link. This is going to be where just the backbone can communicate with each other. So if we added additional provider or provider edge routers down the road, we'd go ahead and configure OSPF on them. So let's go to the command line. All right, you can see here we basically left off from our last video where we put in the base configuration. We put in a loopback address and we put in the IP addressing on the backbone links that go between the PEs. So nothing's changed there. So let's go ahead and start our configuration. Again, we're going to build step by step and test as we go, and I will explain to you what's going on as we go through it. Go to configuration mode and start on our first interface, gig 00. We'll start at the interface level. And the first thing I'm going to do is actually adjust the MTU size. And this is something we need to do for MPLS. It's needed because we're going to be applying additional headers when we're running MPLS. And if we don't, if we had a client connected to our network, if they try to send a 1500 byte packet through, what would end up happening is a lot of times they'll set a DF bit, that's the don't fragment bit inside the packet, and when it got to our router, we'd need to go ahead and apply our additional headers, and there wouldn't be enough room to do it, so we'd end up dropping the packet, and that would break the customer's application. So go ahead and increase the MTU on the backbone interfaces here. These are where the labels are applied. We go ahead and up the MTU. I use 9000. It's a jumbo frame that works well. So we're also going to set the OSPF network type. This is an Ethernet interface, so by default it would be a broadcast type. However, we're just using it in a point-to-point type, so we don't want to actually have a designated router or a backup designated router election happening here. So we'll just put IP OSPF network point to point. And we need to do the same thing for our other backbone link number 2. So we'll go ahead and put an MTU 9000 IP OSPF network point to point. At this point, we are ready to go ahead and start building the routing process. So we'll type in router OSPF1. Now we want to assign a router ID, and this is just the ID that the routing instance will use. So we're going to go ahead and type in router-ID. It's going to be 10.0.0.1, which is the loopback for PE1. All right, so now we'll continue with the configuration. I'm going to throw in some tuning commands here. These are not by default, but they do work really well on MPLS backbone. They'll allow it to scale much better than it would by default. So this is just turning on incremental SPF. And we'll go ahead and use auto cost reference bandwidth 100,000. The reason we do that is because by default OSPF will assign a cost of 1 to 100 meg interface. So whether it's whether it's a 100 meg interface or a gig interface, or let's say it was a 10 gig interface or even higher, then that would always default to 1. So OSPF wouldn't know how to differentiate between those. So what we do is we set the auto cost reference bandwidth. I use 100,000. A lot of people use 100,000, and that will make it so that you can go all the way up to a 100 gig line before you actually have an OSPF cost of 1. So this needs to be done on all the routers, just as it says in the message below. Okay, so we're just setting up the SPF throttle timers. So the 50 is the delay when receiving a change to the SPF calculation, and then the 200 is the delay between first and second SPF calculations in milliseconds, and the 5000 is a maximum wait time in milliseconds for SPF calculations. We'll go ahead and do this same thing for the LSA. We'll use the same timers. All right, and then we're going to do set our interfaces now. So we'll do passive interface default. And what that does is it just, by default, none of the interfaces will try to form an adjacency. So we say passive interface default, then we specifically say what interfaces we want to have come up. So we definitely want to be able to run OSPF across GI00, gig interface 00, and also gig interface 000. And then we'll go ahead and assign the different interfaces to the areas. So if we type in do show IP in brief, we'll see all the IP addresses of the interfaces here. So we'll type in, this is one of the ways to do it, we'll type in network is a wildcard mask. And we'll put him in area 0. We're going to go ahead and put this other interface in area 0. And then we'll go ahead and put the loopback in area 0 also. Okay, so what I've done here is I'm going to type do show run, and then I'm going to go ahead and just grab the configuration using the pipe command with the B variable there. That's begin, then router OSPF. That'll just take me directly to OSPF instead of having to parse through the config. There's different ways to do that, but that's the way that I'm used to doing it, so that's how I've done it. So you can see here, router OSPF, this is the configuration that we've got for it. So we'll look at the interfaces that we configured also. You can see here we've got our MTU of 9000, and our OSPF is network type point-to-point. And again, we've got the same thing for gig 000, MTU and network point-to-point. So we do want these to match. Save our changes. Go over to router 2 now. Set our MTU to 9000. Go to the other interface and set the MTU and the network type again. Let's go ahead and now build our router process. Set our router ID, the loopback on router 2, PE2 here, is 10.0.0.2. Set our OSPF autocost reference bandwidth to 100,000. Let's go ahead and set our tuners to tune this to work a little bit better. Set the LSA arrival for 100. The passive interface to default. We'll go ahead and activate it on gig 00 and gig 000. Now we need to put our interfaces in here for area 0 also. Again, show IP interface brief will show us all of our interfaces, so this is a good way to do it. Put all these in area 0. Now, one thing that is important to mention, and not a lot of people actually understand this, when we put in these network commands, we're actually not saying that we're going to advertise the 10.0.0.20000 network. This is just basically saying that we want these interfaces to participate in OSPF in area 0. So we could have actually put in, say, network 10.0.0.0 and then put in, say, 0.255.255.255 area 0, and that would have covered the entire 10/8 block. So any interfaces in there would have participated in OSPF, but I prefer to do it on a one-by-one basis. That way I know exactly what's going to be in OSPF, so that's how I've done this here. Let's go ahead and save our changes. And let's see if we have a neighbor adjacency now. And we do. So you can see here that we've got a neighbor, PE2, we're on PE2, is pairing with PE1. You can see that our state is full and there has not been a DR or BDR election per our network type point-to-point. And both of the interfaces are working good there. So let's go ahead and go back over to PE1. You can see here that it's working properly. And there's a couple other commands we can do here to just take a look at it, make sure everything is working the way we want. Basically, we know the neighbors are up, so that's a good sign. But we can do a show IP OSPF interface brief. This gives us a really quick way to go ahead and look at our interfaces, see what area they're in, and see what their cost is, and then their network type. And let's go ahead and look at our routing table for OSPF. And here we can see that we've got a route learned. So if the only route we would effectively learn across OSPF right now would be the loop back of the other side. The transports that go between the two routers, let's take a look at the diagram here. These two transports, the 10.0.1.0 and 10.0.1.4, those are locally connected routes, so that's how the router would know those routes. So if we just looked at show IP route, in general, we will see those in there. You'll see that those are connected routes here and here. So at this point, we can go ahead and test that the routing is working. We see the route there to 10.0.0.2, but let's just go ahead and set up a ping across there. We'll source that from our loopback. And there we can see that we actually are able to send packets across. So that's depending on the routing protocol. So at this point, we do have a functional OSPF routing adjacency across both links, which is very good. But at this point, now we want to build step by step. So we want to go ahead and set up some authentication. So now that we know that it's working, we've tested it, we'll go ahead and do authentication. And the reason we don't just, in this case here, put it all together is because if we test after we've put the authentication on and so forth, we may not know why it's not working. It could be authentication, or it could be maybe we've got a bad network statement. So by doing this step by step, then we know exactly where there's a problem if there is a problem. We can validate it and then go back and fix it. So our next step, now that we've got a fully working OSPF system here, is we're going to go ahead and put on some authentication. So we'll do that by going into the interfaces. All right. What we've done here is we've set up a message digest key using key number 1 with the MD5 hash, and then that's our key string. There's different key types, as you can see. There's through OSPF training or going through the Cisco website, you'd see that OSPF has different authentication. It's got a plain text one, and then also this MD5. The MD5 is much stronger, so that's why we use that. Let's go ahead and apply this same thing onto GI 0/0/0. And then our next step would be going into the routing process. And what we want to do is turn this on globally, turn on authentication globally. So we'll turn on area 0 authentication message digest. And you want to make sure that this is authentication message digest. If you just turn on area 0 authentication, it's just going to use the plain text and it won't match the key, and so that would not work at that point. So let's go ahead and go over to router number 2, PE2, and we'll do the same thing. Do this on the next interface, gi0/0/0. And again, we're going to go ahead and go into the routing instance, and we'll turn it on globally there. Okay, at this point, we should actually have OSPF adjacencies again. And we're running full. So we can look at it, show IP OS int. We can run it, and here we can see that message digest authentication is enabled and the youngest key is key 1. That's the nice thing about using a MD5 key there, is that we can always put in additional keys and it'll just roll over without taking the system offline. So here we can see that this is working and it is authenticated. And again, we still have our routes. So let's go over to router 1. Look at GI00 here, and again, message digest authentication is enabled. Youngest key is 1. And on the second interface, we've got the same thing. Message digest authentication is enabled with the youngest key ID as 1. So that's pretty much it for OSPF, but we are going to do one more thing. And inside the MPLS backbone, it's really important to have rapid failover detection. And that's something that's key, because if not, you actually can cause quite a lot of impact to a number of customers, since there are a lot of customers riding over the backbone potentially. So what we'll use is something called BFD, which is bidirectional forwarding detection. And this is a lightweight, extremely fast detection to determine if something's not going right across the link. If that hello is going across BFD from PE1 to PE2, if anything gets interrupted there, really quickly it'll detect it and then notify the upper level routing protocol, in this case OSPF. So the way we configure that is we go onto the interface, we type in BFD, put in interval, go ahead and use 50 milliseconds. The multiplier of 5. So basically we'll send out every 50 milliseconds, we'll be sending out BFD messages, and if we don't get them after 5 attempts, within 5 attempts, then we'll go ahead and we'll shut it down. So in a quarter of a second or 250 milliseconds would be our failover time. Okay, so now we've set it there, but we need to go ahead and put that on the routing interface. So we go into OSPF and we just say BFD all interfaces, and that applies it to all of the interfaces there. So let's go ahead and do that on the other router. And we will go ahead and apply it to the other interface here also. Okay, so now we've got it configured on this second router also. So let's go ahead and test it and make sure that it's working correctly. Okay, and now we see that we do have the neighbors. Show BFD neighbor shows that we do have neighbors and that they are up. And you can see that they are tied to OSPF here by show BFD summary client. OSPF is the client here, and that's working. And we can see here with the show IP OSPF interface GI00 that BFD is enabled. And this side also. Okay, so now we know that it's working. So back to here, now we've got OSPF across these links. Authentication set up, BFD is set up, and it's across both links. And I put 2 links in here on purpose in the lab. That way we can actually see the failover occur. So we'll run a test here in a second to show how that works. So let's go back to PE1. To test BFD, we're going to go ahead and just run a ping test between router to router, at which point I'll go ahead and I'll disconnect the cable on the active link. So, we have 2 links as we see in the diagram, but one link will be the one that's chosen for actually transmitting the data. So let's go ahead and find out what that is. All right, so if we're going to ping, we're going to go from our loopback 10001 to PE2's loopback of 10002. And we can see that the traffic's going to be sent out gig 000. So when we run this test, I will disconnect it. The reason I disconnect it and not just shut it down is because when you shut something down, actually the routers will send out goodbye messages and indicate to the neighbors that it's going down. So you wouldn't get an accurate test. So in this case, we'll go ahead and we'll run a test and we'll see how it goes. We'll set a timeout of 1, which is the lowest timeout that we can set here. And we'll go ahead and ping it. Actually, let's ping this set 5,000. Okay, so let's go ahead and run this. Better set the right loop back there, loop back 0. I pulled it. You can see we dropped one packet and it waited a second for it to respond. So that actually failed over in about a quarter of a second. You don't see it because the lowest response we can see there is 1 second. But you can see here where it was going along, and then it stopped. That was where we pulled it. And BFD saw that right away. Now the thing that's nice about this is BFD detected it that quickly. If we just relied on the routing protocol, we'd actually be waiting for quite a while. So you can see here that the configured timers by default are a hello of 10 seconds and a dead time of 40 seconds. Now you can actually go in and set your timers lower than that to be sub-second, but then it puts a lot more load on the router. So BFD does work a lot better. So in this case we use BFD. It's much more scalable. It's much better for an MPLS environment. In fact, it's a lot better for a lot of environments. So I am a big fan of BFD. So that's it for now on this section. We've gone ahead, we've got OSPF working, our backbone is working, we've got rapid fail detection, and then we'll continue our videos.